viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am from Department of Computer Science, Arabic College, University of Delhi. So in this series of our operating system, presently we are learning the topic of deadlocks. In our previous lecture we have seen what is resource allocation graph, and also we have seen one of the examples of that resource allocation graph. So today the agenda of the lecture is how is this resource allocation graph is going to help us in case of deadlock. So before going to the agenda, let us have a quick recap with the help of a small example about the resource allocation graph. So resource allocation graph, as we can say, as seen on the screen, is basically a directed graph in which there are two types of resources. P1, P2, P3 are representing the resources of process, representing the vertices of process type, while R1 and R2 are representing the vertex of the resources type R1 and R2, which are the resources, are being shown here with the help of a rectangle, while the processes are shown with the help of we can say circles. And the single dots or the single circles within the R1 and R2, within the rectangle of R1 and R2, are showing the single instance availability of R1 and R2. That means these are not the multiple instance resources. Now what is the situation here? That this R1 is already allocated to P1, which is being indicated with the help of edge from R1 to P1, and R2 is already indicated to P2, and this is also we can say shown with the help of an edge from the resource R2 to P2, while P2 is looking for R1 with the help of an we can say request edge, which is from P2 to R1. Similarly, P3 also needs R1 and P3 needs R2 as well. So P3 there is a request edge from P3 to R1 and also from P3 to R2, and the assignment edges are from R1 to P1 and R2 to P2. So this was we can say a quick recap or recap in a nutshell of the resource allocation graph. So here we have seen that process P1 is holding an instance of the resource type R2 and is waiting for another resource type of R1 we can say. Then P2 is also holding an instance of the resource R1 and an instance of R2, and this is waiting for another resource R3, and so on and so forth. So this whole situation is depicted in the form of this resource allocation graph. Now coming to what is the significance of this resource allocation graph in terms of deadlocks. So in order to we can say monitor the deadlocks, or in order to detect the deadlocks, we look for the presence of cycles within this directed graph, which is resource allocation graph. If the graph contains no cycle, then we can say that no process in the system is deadlocked, and if the graph does contain a cycle, then a deadlock may exist. Now why I am saying it may exist, because even in case of a cycle, if if this resource allocation graph is consisting a cycle, then there may be a deadlock, or it may it may not result in a deadlock. How? We are going to see in this lecture. So for example, if each resource type has exactly one instance, then a cycle implies that a deadlock has occurred. And in our previous lectures we have seen that in order to understand the situation of deadlocks, or in order to monitor the situation of deadlocks, the number of instances of the resource is having a very we can say important place. So if each resource type has exactly one instance and then there is a cycle, that means the cycle implies that a deadlock has occurred. Now if the cycle involves only a set of resources, each of which has only a single instance, then there is surely a deadlock. So we can say For example, in this situation in which the cycle involves the set of resources for which only a single copy is available or only a single instance is available, then each process involved in this cycle is going to be a deadlock. In this case, we can claim that a cycle in the graph is both a necessary as well as a sufficient condition for the existence of deadlock. And what is the we can say a situation? The situation is that all the resources in the resource allocation graph are having only one instance. So in this situation, a cycle, if it is occurring in the graph, is both a necessary as well as a sufficient condition for the existence of deadlock. How? This we are going to see with the help of an example. So here let us consider the resource allocation graph, which we have already seen in our previous lectures. We have 4 resources and 3 processes, and R2 and R4 are with multiple instances. R2 is having 2 instances and R4 is having 3 instances. So if we can try to look out the possibility of we can say cycle in this graph, are we going to find any cycle here? Let us try to kind of examine. So there is an edge from P1 to R1, then from R1 to P2, and there is also an edge from R2 to P1. So R2 to P1, then P1 to R1, R1 to P2, then there is no edge from P2 to R2. That means in case of here in the first kind of we can say a rectangular or between P1, P2 and R1, R2, we are not finding any cycle. Then if we consider the edges starting from R2 to P1, then from P1 to R1, then from R1 to P2, P2 to R3 and R3 to P3. That is also kind of we can say it is not giving any cycle here. Now let us consider the situation that let's say R2 is only having a single instance. So in case of single instance, either it will be kind of given to P1 or it will be given to P2. So what will be the situation if there is only one instance of R2? So, and I am assuming here that this R2 is already being assigned to P1. So there is from R2, there is an edge from R2 to P1, then from P1 to R1 is there, from R1 to P2, and then why? Because the P2 is looking for the resource R2. So from P2 to R2 there will be an request edge. So from this is going to give me a cycle between these 4 vertices, which are R1 and R2 and P1 and P2. But now as there are multiple instances of this R2, one of which is given to P1 and another one is given to P2, here we can say that there is no cycle if we consider these resources which are R1, R2 and P1, P2. These resources and the processes P1 and P2. So if we can see here, if the process P3 requests an instance of the resource type R2, then what will happen? Then there is going to be an edge from P3 to R2. Now consider the cycle from R2 to P1, P1 to R1, R1 to P2, P2 to R3, R3 to P3 and P3 to R2. Then it is going to result in a cycle. Why? Because there are only 2 instances of this resource, and the third process is also looking for that particular resource along with the interdependency on other processes which are holding the resources. So if a process P3 is going to request an instance of the resource type R2, currently we don't have any extra instance which is going to fulfill this request. Then in this situation there is going to be a request edge from P3 to R2. So as the resource has requested, as the process has requested the resource, there is going to be an addition of a request edge from P3 to R2. Now there will be two cycles in the system, P1 to R1, P2 to R3, R3 to P3, P3 to R2, and then R2 to P1. This is the we can say bigger cycle, and then there will be another cycle which is from P2 to R3, R3 to P3, P3 to R2, and R2 to P2. So here we can see this both of these cycles starting from P1 ending to P1 and starting from P2. So from P2 to R3, R3 to P3, then there will be an additional edge which we are going to add here corresponding to the request of R2 from P3, which is P3 to R2 edge. So P2 to R3, R3 to P3, P3 to R2, and then again from R2 to P2. So there will be minimum 2 cycles which will exist in the system if we are going to add one more we can say request edge starting from P3 to R2. And here is the we can say that situation. So here is the resource allocation graph which is with the cycles, and here we have added this edge which we were talking about from P3 to R2. Now here you can monitor 2 cycles very easily. Now if we talk about next thing, that means if we talk about, let's say multiple resources. So here in this situation till this point processes P1, P2 and P3 are, we can say, deadlock, because P2 is waiting for R3, R3 is being held by P3, P3 is waiting for either process P1 or process P2 to release this resource R2, and in addition P1 is also waiting for process P2 to release the resource R1. So here is going to be we can say there is a presence of this cycle. Now let us say we have one more resource allocation graph which is shown in this figure. So here we have two two resources R1 and R2, and each of the resource R1 and R2 are having 2 instances of each, and there are total 4 processes P1, P2, P3 and P4. So what is happening in this graph, let us try to understand. So P1 has requested for R1, while the 2 instances of R1 which are available with the system are being assigned to P2 and P3 already. Then P3 is also requesting for R2, while the 2 instances available of the resource R2 are being assigned to P1 and P4. This is what the situation which is happening here. So in this example we also have a cycle starting from P1 to R1, then from R1 to P3, P3 to R2, and then from R2 to P1. So that is also a cycle which is available here, or which is present here, we can say. But please notice that there is no deadlock, because the process P4 may release the instance of the resource type R2. One of the resource type, instance type of the resource R2 is available with P4. Now P3 has requested for R2 and is waiting for that particular resource to be released. Now if P4 is going to be we can say release the resource R2, that instance will be acquired by P3. So even if there is a cycle which is we can say which is very well visible here in the resource allocation graph, the deadlock may or may not exist, and the sole reason here is availability of multiple instances of the resource type R2. So then there is no deadlock, because the process P4 may release its instance of the resource type R2, and that resource can easily be allocated to P3, and that will ultimately break the cycle. So even if we have one cycle present here, this may result in ending the system, or in having the system with no deadlock. So we can see that if a cycle is being formed in a resource allocation graph where all the resources have the single instances, then the system is going to be definitely deadlocked. While in case of resource allocation graph with the resource type of where the resource are of multi-instance type, cycle is a necessary condition of the deadlock, but it is not the sufficient condition of the deadlock. While in case of the single instances resource type, all single instances resource type of the system within the system, then the cycle is also a necessary as well as a sufficient condition. While in case of a multi-instance resource type system, cycle is a necessary condition, but it is not the sufficient condition. Now let us try to see one more example in order to have kind of a deeper clarity here. Now here we have three processes P1, P2, P3, and there are three resources R1, R2 and R3, and all these resources are having single instances each, which can be observed by the figure very clearly. As there are no dots, or there are no rectangles within the instances of R1, R2, R3, the resources are having single instances. While the situation of P1, P2, P3, if we observe, so P1 has requested for R1, R1 has already been given to P2. Along with holding this R1, P2 has also requested for R2, that R2 with its single instance has been given to P3, and P3 along with kind of taking this R2 has also requested for R3, where this R3 is we can say is given to already given to P1, which is shown with the help of this long edge starting from R3 going to P1. And please note that here R1, R2 and R3 are having single instances of all these resources. R1, R2 and R3 are having single instances. Now here with these single instances we have that this is going to result in case of a deadlock, because the cycle is also existing here. So this is an example where with the single instances of the resources along with the presence of the cycle, the system is going to end in a deadlock. So with this resource allocation graph, there is also we can say one more kind of a supplementary tool we can say, which is available in order to study the deadlocks, and that tool is basically about kind of we can say allocation matrix. And along with the allocation matrix we have one more matrix which we are going to see now. So till this point let me we can say let me recap this lecture. So we have seen that we have seen one example of resource allocation graph, and with this example we have also seen that what is the significance of having these cycles within this resource allocation graph. So if all the instances in the system are all of single instances type, and if there is going to be a cycle, then the system is deadlocked. System may or may not enter into a deadlock if there are multiple instances of the resources. So cycle is definitely, yes, it is a kind of necessary condition for the deadlock, but it is not the sufficient condition in case the resources are having multiple instances. So with this let us try to explore one more tool which is betterly known as allocation matrix. And this allocation matrix, as I have told you, is kind of can be formed by using the resource allocation graph of a system, and that's why I have told you that this is kind of a we can say a supplementary tool which is used along with this resource allocation graph. So in allocation matrix we are going to there will be a entry which is going to be made for each of the resource assigned. So here we are going to kind of take the stock of what is being assigned within the help with the help of a matrix. So for example, if we can see the following matrix in which an entry is being made in front of P1 and below R3. So P1 is we can say the row heading, and R1, R2, R3 are the column headings. So R1, R2, R3 are representing resources. So if we are going to give this is kind of, we can say it is a binary matrix, or we can say it is having the values as 0 and 1. So if there is a 0 in one cell, that means that process has not been allocated with the resource. So here we can read here it as the resource R1 and R2 are not being allocated to P1, while the resource R3, because it is containing 1 in the cell adjoining P1 and R3 or intersecting P1 and R3, it is containing a 1, the digit 1. That means this resource R3 is being allocated to P1. So similarly, if we can see the second row which belongs to the process P2. So this process P2 is being allocated the resource R1, not the resource R2 and R3. Similarly, if we go with P3, we have the resource R2 which is being allocated to P3 and it is indicated by a digit 1, while R1 and R3 are having 0 here. So with the help of the presence of the digit 1, we are going to show the allocation of that particular resource to the process. So in the following matrix, an entry is being made in front of P1 and R3. So that means R3 is assigned to P1, and we have also seen this whole matrix as a complete entity. Then apart from this, we have one more kind of tool which is known as request matrix. So in the previous matrix, which were allocation matrix, we have seen which resource is being allocated to which particular process. Now if we want to see the status of the request, that means which particular process is requesting which of the resources, that is going to be we can say shown with the help of the request matrix. In the request matrix, an entry will be made for each of the resource requested. So that means the cell which is intersecting the resource, a particular resource and a particular process, if that resource has been requested by that process, that entry in the cell will be marked as 1. So in the following example, we see that P1 needs R1, therefore an entry being made in front of P1 and below R1. And here is this request matrix, if you can see. So there is an entry 1 in the cell of P1 and R1. So that means the process P1 has requested R1 and it has not requested R2 and R3. Similarly, if we see the second row, if you observe the second row corresponding to the process P2, it has requested the resource R2, not the resource R1 and R3. And if we talk about P3, it has requested the resource R3, not R1 and R2. So this is what the situation of request matrix is. Now here is we can say there is an analogy which can be made here, that the request matrix is having all the we can say all the cells having the number 1 where there is a request edge. Similarly, if we talk about the allocation matrix, in the allocation matrix, although all the cells which are having 1 as the digit in them are representing an assignment edge. So we have already seen that if a resource allocation graph does not have cycle, then the system is not in a deadlocked state. But if there is a cycle, then the system may or may not be in the deadlocked state, and it is very important to deal with the deadlock problem. This is this observation is going to be very important when we kind of drill down into the deadlocked system or deadlocked state more. So here with this allocation matrix and the request matrix, we can say that neither we are having any resource available in the system. Now let us consider that the scenario that we don't have any more resources available in the system, and nor a process is going to release this. So neither we are having any resources available, that means the availability of the resources is, we can say, 0, and the process are also not going to release the resources. And then in this situation, each of the process needs at least a single resource to complete. Therefore, they will be continuously holding each one of them. How? Let us see. So for example, in the resource matrix, we have seen that the process P1 has already taken the resource R3 and is kind of waiting for the resource R1, which is available, or we can say which is shown with the help of this request matrix. Similarly, process P2 has requested for R2 and has already taken R1, while P3 has taken R2 and has requested for R3. So, and availability of the system is 0. That means we don't have any resources available in the system, and processes are also not going to release. That means this is going to create, we can say, a deadlock, because each of the process needs at least one resource to complete, and they are holding the another resource also, and we cannot fulfill the demand of at least one process using the available resource. Therefore, the system is deadlocked, and this deadlock is also determined or also seen when we detected a cycle in this graph. So we can say the metrics are also the tool to detect the deadlock or to determine about the deadlock, while the resource allocation graph presents that particular information or the whole scenario in the form of a in a pictorial form, in the form of a graph. So here in this lecture, what we have seen is, we have started with a small example of resource allocation graph. Then we have seen the significance of cycles in detection of deadlock, that when this cycle is going to be the necessary condition, when this cycle is going to be the necessary and sufficient condition for the detection of deadlock. Also, we have seen the supplementary tools, namely allocation matrix and request matrix, and their utility in determining about the deadlock. So here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed the lecture. Thank you for patient hearing. Goodbye. I'll see you in the next lecture.